So, hello, good afternoon. Thanks for coming, Peter. So I'm going to talk about my talk title is Symmetry and Convergence. The paper I'm going to talk about has a slightly different title. It's on arXiv, and this is joint work with my former PhD student, Morgan Town, who's now junior faculty at Howard. So the way this problem started, that I started thinking about this circle of ideas, is a couple of years ago, I was interested in this problem here, where so somebody gives you a data set that looks like this, so just some large graph, and you're told this is a small part of a very large graph. Yeah? In this case here, this is a small part of the link graph of Facebook. So the problem is you get some small part of a very large structure, and you want to learn something about the large underlying structure from the data you have. Okay? So if you think about this in terms of statistics, if you think about Facebook being a very large random graph, and this here is some small part of it, then this is a sample of some population, and sample size is graph size. So if you see more data, you don't see more graphs, you just see one graph that grows. So, and now, can you learn anything from this graph here about what the underlying structure? So if you want to do that, then you have to solve various problems. You have to think about, first of all, how do you, if you, let me start like this. This is going to be a very theoretical talk. And the kind of results that I'm going to talk about are limit theorems. Yeah, so let me just recall briefly at a cartoon level what these limit theorems look like in the case of i.i.d. sequences, in a very classical case, right? And then basically this tells us where we're going to head. So if you consider an i.i.d. sequence, x1, x2, and so on, I'm going to call the whole sequence like an infinite i.i.d. sequence, or we're just going to call it x. Yeah. So, and then I have a function f that I can apply to an element of the sequence. So, and now I can compute the sample average, right? Statistics 101. Yeah. So, and now the basic basic theorems of statistics tell me that this sample average converges, basically, right? And what they say is the law of large numbers says that the sample average converges to the expectation of f for an i.i.d. sequence, right? That convergence happens almost surely, so that tells me that if I use this as an estimator of the expectation of f, it's strongly consistent, right? So consistency would be convergence in probability. This is almost sure convergence that implies in probability. So it's strong, what's sometimes called strong consistency. So then I have the central limit theorem, which gives me an asymptotic rate for that, right? Which tells me if I scale this, the error, the estimation error here, by square root of n, then that is asymptotically normal in the sense that it converges to, in distribution, to a standard normal variable times some scaling factor. And the square, this is something like an asymptotic standard deviation. The square of that is usually called the asymptotic variance. Yeah. So, and then I can, under certain conditions, I can strengthen that further to something like a Berry-Esseen bound, for instance, that says if I take this quantity here on the right, on the left, in the central limit theorem, and compare it to the quantity on the right in terms of some metric. So this is a random quantity, this is a random quantity, I need some metric on probability distributions in order to compare them. That in total variation, this is bounded by some function of n. Yeah, that is a Berry-Esseen type bound. Okay, and basically then in short, what I'm going to talk about here in this talk is that loosely speaking, if instead of the sequence x here, I have some random structure, so graph, an infinitely large graph, an infinitely large matrix, something like that. And that structure has a symmetry property, by which I mean its distribution remains invariant under a certain group of transformations. So there can be different groups, but they have to have certain properties. If that is the case, then these symmetries tell us how we can compute sample averages within the structure And theorems like this still hold. Yeah. So if I look at this graph again, the symmetries will tell me how, if I want to estimate something from this graph in the same way, say I have a function that depends on a small part of the graph, like a few vertices. Number, like, is there a triangle on 3 vertices or not? Something like that. So how do I average that? How do I compute a sample average? I somehow have to average within this graph, right? So how do I do that? I have to explain what that means to have a sample average in the first place. So there's a generic way, if I have the symmetry, there's a generic way to explain what sample averages are. These sample averages converge to expectations in some sense, and they have a central limit theorem. So now I'm just going to throw 2 results at you, and then I'm going to spend the rest of the talk unpacking these results backwards. So the results look like this. So one of them is what we proved, and one of them we imported from ergodic theory. So let me start here at the top. So X is now an infinitely large random structure, graph, sequence, matrix, whatever. Now, I assume that X is invariant under a group of transformations, and this group is infinitely large. That has a reason why it should be infinitely large. We'll come to that. So invariant means its distribution is invariant under each transformation of the group. So if I take the transformations act on the graph, each transformation eats the graph, spits out another graph. And that doesn't change, that changes the graph, but it doesn't change its distribution. So now, then I assume that this group has a specific property, namely, basically that I can approximate this infinite group in a meaningful way by finite subsets. Yeah? So I have the subsets A1, A2, and so on here in the group, they're finite. And they must have satisfied a property like this. We will come to why I assume this property later. But basically what it says is, if I take one of these sets and I apply some element, single element of the group to the set, then this entire set gets shifted within the group. And now I compare it to the set that I put in, right? So I compare the shifted and the unshifted set, how much they overlap. And I want the ratio of that over the size of the original set to go to 1. So basically, what this says is, if I make n large enough, then the set almost doesn't move. Yeah. Okay, so and then I assume that my function here has an expectation under x. Yeah, and that is simply because I want to estimate an expectation, so that expectation should exist. Yeah. So now, if those hold, then I can compute an average like this here, which is I take all transformations in one of these sets here, apply each of them to x, and then evaluate the function. And then I just average. Okay, so my sample average is a transformation average. This converges almost surely to an expectation, which is now a conditional expectation given some mysterious quantity here that I have to explain later. Yeah. But let me just say for now that the conditioning here is what a computer science would call a feature, not a bug. Yeah, this is actually better than if we would have this condition. Because this quantity contains more information than it would contain without conditioning. Yeah. So this converges to expectations. This was proven by Lindenstrauss in 2001. So Lindenstrauss, that's Elon Lindenstrauss. There are 2 famous Lindenstrausses. The great functional analyst Johann Lindenstrauss. Machine learners will know Johann Lindenstrauss because of the Johnson-Lindenstrauss lemma. That's just a small fraction of his contribution. This here is his son. Yeah. So he's an ergodic theorist and got Fields Medal in 2010, I think. So he proved this result here that was originally conjectured by von Neumann 70 years ago, 70 years before this. Then there was a long line of incremental contributions, and it was finally wrapped up by a Fields medalist. So the proof is not trivial, but you can see stating it is elementary, right? Except for this part. So, okay. So now this is from a statistician's perspective. If we write it like this, which is not how ergodic theorists write it, but if we write it like this and look at it as statisticians, this is a law of large numbers, right? It's a strong law of large numbers, but it's almost true convergence. So, and then basically the result that I want to talk about that we proved on top of it is the central limit theorem for this law of large numbers. Yeah. So what that says is if this function also has a second moment, and if it has some property called conditional mixing that I have to explain later, then the difference between the two sides here, yeah, so the estimation error is asymptotically normal if I scale by the square root of the size of the set that I have. So it's again the square root of the number of summons in this set. Yeah. So and we have like on the previous slide I also had this Berry-Esseen bound. We have a Berry-Esseen bound too. We also have concentration under more restrictive conditions, but I'm just going to only talk about central limit theorems because that's the most important part. Yeah. And I have 16 slides. I can easily spend an hour talking about 5 slides, so we would just see how far I get. Yeah.
Can I ask?
Yeah.
So, you're not explicitly assuming that AN is a subset of AN plus 1.
No.
Okay.
Yeah. I mean, for the most examples in common practice it is, but there are actually kind of pathological examples where it's not required. Interesting. Yeah. So here's the result again. And now I've highlighted a couple of parts in blue here. Those are basically the parts that I have to explain one by one throughout the talk. Right? So I have to explain what it means that in more detail, how we can visualize this invariance under how we should envision that. What this condition here means, then what this conditional mixing condition means, what this average means, and what it means to conditional disaggregating. So in the central limit theorem, we have the convergence is to, again, a normal variable times the scaling factor. And the scaling factor is now a random quantity, this asymptotic variance. And we have an explicit expression for this. So it looks like this in the general case. I just want to mention here, like for those of you who are used to central limit theorems, this is surprisingly simple, this expression. So often when you prove central limit theorems with not just i.i.d sequences, some form of dependence, what becomes very hard is, so either you cannot evaluate the asymptotic variance at all, or it becomes prohibitively complicated. And something that we see in these results, also in all the examples that we have looked at specifically, where we have evaluated this like more specifically for a specific type of function or specific type of variance, is that every time we get a very clean expression for the asymptotic variance. So this seems to be a hallmark of these problems with group symmetry, that they give you simple asymptotic variances. So first of all, let me talk about this estimator. Yeah, so to see what we're doing at all, kind of procedurally, and then we can talk about the conditions. Yeah. So given is this function f, and then this very large structure x. And a very useful way to think about that, which is mostly the case usually in actual problems that you consider in practice, is that this function f depends only on a very small part of the structure. Yeah. So think of that as I've plotted an example here where my structure is a random field on the grid. So think of the grid as it's tending infinitely in all directions. Yeah. And now I have a function that depends only on the smallest possible part, maybe just on a single grid cell or a single random variable of this grid. So I graph the domain of this function as this little gray window here. Yeah. So to basically apply this function to the grid means I read out the value at this one point, plug that into my function, and compute the value. So and now I observe a somewhat larger but finite part of x of this infinite structure as a sample. So here, let's say it's like this 3 by 3 part of the grid. That's my sample. So now I want to compute an expectation for f. Now, if these variables here were independent and identically distributed, then I would just average over them, right? They're not, but I mean, I could still try to do the same. It's basically the best thing I can come up with, right? So I could move my window here to each point in this grid and just read out the value and average. Yeah. Now, that operation, I can write that in a slightly different way, namely by leaving the window in place and moving the grid instead. So I apply a shift to the grid and move it down instead of moving the window. Yeah. So in that shift that I apply here, that is my one of my transformations in my group. Okay, so that way I think of these sets AN that I average over in my estimator here as all transformations that I need to cover my sample with, like, reach every point in my sample with this little observation window. And then the group is all those transformations that I would need to reach every point in the infinitely large structure. So that way, this set here and this index n correspond to sample size, except that the sample size is not n, it's the size of the nth set, and that could grow larger than more quickly than linearly. Right? So in this case here, for instance, if n is the edge length of the grid I've observed, then it goes quadratic. So okay, so then my estimator just looks like this in this case, right? And basically, one way to write it is as so my function f that this function f that I apply to the infinite structure is really the application of some function of an individual point here to a part of it, right? So I call, let's say I have a function g that just takes a real value as input, a real number as input, and these are real value variables here, right? Then the function f, which is formally a function of infinitely large random fields, right, is evaluated as evaluating g at a single grid. Yeah. So, and then this average would be the average over all shifts of this 3x3 grid applied to g, right? And then I have to divide by 1. So, okay. So, one example of that are, like, one of the basic examples are exchangeable sequences. So here x is again a random sequence as on the first slide. So but now I'm assuming not that it's i.i.d, but that it's exchangeable. So that means if I apply any permutation of the natural numbers to its indices, then its distribution doesn't change. So that is exactly, for those of you interested in basic statistics, that's of course exactly the setup of the EXCHANGEABLE theorem. Now, here in this case, what does this moving the window mean? So here here's my sequence that I start with, and now I again have a function f that depends only on a small part. So the simplest version is it depends only on the first entry, right? Some function g of the first entry. So and now I apply a permutation to x. So let's say my permuted sequence looks like this, right? Then f of the permuted sequence would be g of the first entry of the original of the permuted sequence, and the first entry of the permuted sequence is the third entry of the sequence. So basically that way I use permutations to swap different elements of the sequence to first place and read them out there. That's what the estimator does formally. Yeah. So and in this case, if I compute the average over this here, right, then I notice that actually there's some cancellation going on. So now in this case, it turns for these permutations, because I have to check which sets here satisfy my conditions. But it turns out that in this case, I can use the set of permutations of n objects. Okay, so an is a set of all permutations of n, of the numbers 1 to n. So that set, of course, that is here, the set Sn. That set, of course, has size n factorial. Yeah? So the sum here has n factorial sums. Yeah? But so here I've written it out. But then I see that because each of the first n elements gets swapped to first place more than one time, namely n minus 1 factorial times, I have a lot of redundancy here. And the sum, there's cancellation, and the sum over n factorial elements collapses to a sum over n. Yeah, and this is exactly, here's of course exactly the sample average, the normal sample average for i.i.d sequences. Okay, so and what is the connection to i.i.d sequences? I'm not going to get, unfortunately, I don't have time to get into that, but for those of you who are familiar with the Finnetti's theorem, yeah, the Finnetti's theorem says that an exchangeable sequence is conditionally i.i.d. So there's some random distribution that you select at random, and then you sample x1, x2, and so on, conditionally independently from that distribution, right? That's the Finnetti's theorem. So, and here in this case, it turns out that conditioning on this ergodic component, which I haven't explained yet, is exactly conditioning on this distribution here. So what does it mean? That means that the convergence that I get to the ergodic component means that that thing that I end up estimating, this quantity I end up estimating, this conditional expectation, is the expectation under this unknown but true distribution of the data, basically. So I can recover properties of this unknown view by estimation. Yeah. So, and that's why I like that already hints at why I said that this conditional expectation actually contains more information. Like why this is good for us, because we can recover this objective or aspect of this object, right? This was an unconditional expectation. So, and then the central limit theorem takes this form here. So this is just the, I'm not sure what I've done here. Yeah, so think of this as some asymptotic variance times z times a normal variable. Yeah. So this is just the basic central limit theorem for i.i.d. sequences, right? And the reason for that is the Finetti. So basically, we're conditionally i.i.d, so conditionally we get back. Right? So that's not very interesting, but it's illustrative, right? It tells us like what the connection is to this case. So now a more interesting case that relates to my graph example is you can also define an exchangeable graph, right? So this is in an exchangeable graph, we think of the graph X, this is my infinitely large graph. We think of that as given as its adjacency matrix, right? So it's an infinitely large matrix. And we call it exchangeable if applying a permutation to the rows and the columns simultaneously in that matrix leaves the distribution invariant. So in a graph, that means I'm permuting, I have labeled vertices and I'm permuting those vertex labels. Yeah, and that leaves the distribution invariant. So now, if I have a function of the entire graph that is computed by computing, like, say, the function of the subgraph of the first three vertices, right? This could be, say, the indicator function of is this a triangle? Say. Then I would start with my graph here, then I would apply some permutation, and I swap these labels here. And so now I evaluate f on the permuted graph. So G reads out the vertex, the labels 1, 2, 3, right? So here 1, 2, 3 is now a different subgraph. So in that way, I'm averaging over all these possible subgraphs. So and then I again get the central limit theorem. You can see that the normalization of this average is now slightly different. Again, what happens here is that things collapse out because I have repetitions. But now, because of the combinatorics of these three nodes here, I get slightly different normalization. But otherwise, it still looks the same. Yeah. So, and then again, here I have something given an ergodic component, and that I still have to explain. Okay. So, questions so far? Or, yeah.
There's maybe something in the chat.
Yeah, that is exactly true. So somebody asked in the chat whether the ergodic component will be the graphon. That is right. So if you know what a graphon model is, a graphon is a way to parameterize random graphs. Yeah, it's like a type of function that parameterizes a random graph. For these exchangeable graphs, the ergodic components are exactly those distributions that are parameterized by graphons. So what this tells you is averaging like this lets you recover information about the underlying graphon. If you're not familiar with graphons, but with stochastic block models, that's a special case of that. Same thing with stochastic block models. And that is actually how, in a way, how this work started when a couple of years ago, when we were working on graphons, with me and plenty of other people, one thing that kind of one bigger picture that emerged is that a lot of similarities showed up in like how you treat these things statistically. Statistical techniques you can apply to these models were somehow very similar to those that appear in classical statistical problems. And at some point I felt this just can't be all coincidence, right? There's something underlying, there's something deeper going on. So, okay. See if this is a viewport.
Oh, you got something else in the chat now.
So are we allowing the group to be uncountably infinite? So yeah, very good question. Yes, in principle, we allow the group to be uncountably infinite. I'm skipping about that here because if this is uncountable, the sum becomes an integral, and then I have to explain how to integrate. Yeah, so for those of you who are familiar with this group is always locally compact and second countable. It has a Haar measure, and we can integrate that Haar measure. Yeah, but to just keep notation simple, I stick to the countably infinite. So going back to the result, so we've looked at this. So now we're just going to look at the other conditions. Yeah, and the first thing is this invariance. So we've already seen two examples, right? So in general, the random structure is symmetric or invariant if it is invariant under all transformations. If its distribution is invariant under all transformations in some group. So and for our purposes, one way that enters here directly is that if that is true, then you see immediately that these transformations leave the expectation invariant for any function, right? So, and if you think about what we're doing here, basically the way we collect information by transforming something about the expectation, right? Why is there hope that that might work? Well, because this actually leaves the expectation invariant, right? So then the only thing that could get in the way is the dependence between values. So now for exchangeable sequences, right, that invariance is this invariance under permutations of the index set, right? But other examples of symmetries are all forms of exchangeability, which are always the exchangeability, just always the name applied whenever something's permutation invariant, right? So that could be sequences, graphs, more generally arrays, which are basically matrices and generalized matrices, right? Partitions, random measures, and so on and so forth. Then stationary sequences and random fields. So that is shift invariance under some group of shifts, right? Stationarity. Then there are translation and rotation invariant random fields, and I mean that's just a start. But it is in a sense, these two examples from a technical perspective, exchangeability, so permutation invariance and shift invariance are kind of in many technical ways two opposing poles of the spectrum of how things work. Things that work for one of those don't work for the other, and vice versa. So it's always like if you have something that covers both of these cases, then you have a pretty good theory. We have actually, it turns out that thanks to the ergodic theorists, we have an even larger theory, but this already maps out a lot of between them, a lot of the pathological cases. So now there's this condition called this condition on the group here, right, which says I approximate the group by finite subsets, right? So basically, if you step back for a moment and think about what we want to do, basically the idea is we replace the sample average by a group average. But the group is infinitely large, and it has to be infinitely large because we want asymptotics, right? We want to have some form of convergence. Basically, the size of these subsets corresponds to sample size, so we really need them to grow infinitely large, right? There's so otherwise it's not going to work. So now what this condition says, or what we want, roughly speaking, is we want to, since we can't average over an infinitely large group, we want to approximate that infinitely large group by averages over larger and larger subsets, right? So, and why do the subsets, why should they satisfy this condition? And first of all, you can see that if I plug in the group here, then this is 1, right? So if I apply any transformation of the group to itself, it just shifts the group in itself, right? So this here is 1, so that's 1. Okay, and this should get closer and closer to it. But there's a slightly, specifically for estimation, there's a slightly different intuition that I find helpful. So if you think just that this sample average, right, or this average over AN, that this, just assume that this is in some sense a valid estimator of the expectation. Yeah. So that means that if N is large enough, this value must be approximately this value. However you measure approximately, not important. Yeah, but somehow this value must be similar to this value. So that must be similar to the expectation. If I then transform, that is the same as the transformed expectation, right? And so that must be similar to the transformed average. And that basically means I'm shifting the set here in the average. So I have to make sure that this and this are approximately the same, otherwise it can't work. Yeah? And one way to ensure that is by ensuring that shifting the set here basically doesn't change. It hardly changes, and that is what this condition says. Yeah. So not every group contains a sequence of sets like this. And if it does, it's called, there's a specific class of groups, and they're called amenable groups. And these amenable groups play a big role in ergodic theory and in group theory. And there are different ways to, I mean, this is one explanation of it, but there are other ones. Another way to look at these sequences is that they are geometrically efficient in the sense that the volume of these sets, so the surface of these sets is small compared to the volume. Yeah, and that is now, if we want to prove things about dependent random variables, it's basically that gets you very close to an isoparametric argument. Yeah. So it's not, that's not coincidence. Okay, so examples of groups that have this property are permutation groups, then shift groups, so both countable shift groups and uncountable shift groups, so Euclidean groups, which means also rotations, but then also plenty of others like Heisenberg groups, like automator groups, and so on. Right. So, so we've looked at invariance, we've looked at this condition here, we've looked at the sample average. So now we have to get to the ergodic components and to conditional mixing. So,
sorry, can I?
Yeah.
So about this assumption, it doesn't, I mean, just from naively looking at it, it doesn't feel like it would have to be that the size of AN goes to infinity without, I mean, where is that part in that? Is it in the psi, or the fact that size is an uncountably large, there's an infinite number of possible transformations?
That this doesn't seem to say that the size of these sets has to diverge.
Yeah.
Yeah, that's basically, you cannot construct something like this in an infinitely large group without this. So
right, yeah.
If this group is compact, then indeed, yeah, these sets, like you can just choose each of the sets as a group, right?
Yeah,
and it works, right? But if the group is infinite, then you don't get this without, then you can always move it somewhere, basically, right? You can always move it out of that set. Yeah. So basically, these groups can be uncountable, but they're always, as I said, they're always locally countable and second countable locally compact. So they have a geometry, if you will, right? This geometric intuition that you take something, they have a shift invariant metric and a shift invariant volume. So if you take a compact set and you shift it far enough away, it will move out. Okay. So now for this ergodic component, this goes back to results that, so to a result of Varadarajan that's very old from the 60s, 1963. And then there was a whole list of results. There's an absolutely marvelous paper about it by Duncan in the late 70s. And this paper connects this to the statistical concept of sufficiency, conditioning, in the sense of conditioning on sigma. If you're into that kind of stuff, read this paper. It's favorite. I've never seen. I mean, for me, this paper is the last word of mathematical elements. Right? I mean, Duncan is always, the way he proves very deep results in half a page from first principles is just, I mean, inimitable. Like this paper is particularly beautiful. So it's called Sufficient Statistics and Extreme Points. But now back to our problem here. So what the ergodic decomposition theorem that was first proven by Varadarajan says is, if you have a locally compact second countable group, then the set of all its invariant probability measures, so all distributions that are invariant of it, is a convex set. So think of that as a subset of the set of all measures on a space. Those that are invariant are a convex set. That is true for any group. That's even true for a single transformation family. They're convex. But the extreme points of this are the so-called ergodic measures. And now comes the actual statement of the theorem. So you can, any invariant measure can be sampled as follows. You select one of the ergodic measures of these extreme points at random, and then make draw from that ergodic measure. Okay. So somebody asked earlier about graphons. If we look at the set of all distributions of random graphs that are invariant under permutations, then that is a convex set of distributions. The extreme points of that convex set are exactly those that correspond to graphons. And the way you sample from an exchangeable graph is by selecting one of the extreme points at random. So select a graphon at random and then draw from the graphon. In De Finetti's theorem, the set of all distributions of random sequences that are invariant under permutations is convex. The extreme points are the i.i.d distributions. And the way you sample an exchangeable sequence is you select an i.i.d distribution at random and then draw i.i.d from that distribution. Yeah. So, and so the meaning of the technical meaning of Berry-Esseen is a little hard to explain. I mean, the first time, I've never met anybody who saw it first time what it means, like the first time they saw the definition, but I'm just going to briefly sketch it. So the definition is, if you look at a set that, so if you look at an event, so some measurable subset of your space in which your graphs live, or the sequences or whatever, if you look at an event in your sample space, then you can say that that event is invariant under your group if each transformation applied to that set gives you the same set, right? So in a space of sequences where you apply permutations to the entries, this basically means you're permuting x's in your product space, for instance. Yeah? So if that doesn't change the set, then it's an invariant set. So, and the ergodic distributions are the ones for which each of these invariant sets has probability either 0 or 1. Happens certainly or happens certainly not. Yeah. It's kind of hard to see why the invariant sets are the ones we should care about, and I'm not going to try to illustrate it because we're just in too much of a digression. But just vaguely speaking, since we care about statistics and estimation, this probability 0 or 1 thing here is important because we're trying to estimate something from a single instance of a large object, right? And so basically we have to be able by whether an event happens, if we can decide whether an event happens or not, if we would see one entire large graph, the complete infinite thing, we would be able to tell which sets it's in or not, right? And so if that set has probability 0 or 1, then we can tell something. And now on top of that, we also don't see the entire thing, so we have to approximate by convergence. Yeah? Okay. So, but basically the conditioning on this ergodic component turns out to be the same thing as conditioning on the invariant sets. Okay. So that's a definition. If that doesn't really go down right now, then don't worry about it. I certainly didn't get it the first time. So what's more interesting maybe is to look at it in terms of examples, because kind of the pattern there is that we have some random invariant random structure. Then you have the invariant distributions, and the ergodic ones are somehow the most interesting ones each time. Yeah. So in the case of sequences nx by n that are exchangeable, it's the i.i.d. The ergodic distributions are the i.i.d. distributions. So that's De Finetti's theorem. Then exchangeable graphs, the ergodic distributions are those given by graphons. So that's the Alves-Huber theorem, right? There's Kingman's theorem, which tells us the exchangeable partitions are the ergodic distributions, are so-called paint-box partitions. If you have a discrete time Markov chain where the invariance is stationarity, the ergodic distributions are the irreducible chains, and so on and so forth. Yeah. So general pattern is as a subset of the set of all invariant distributions under some group, you have some subset of particularly interesting ones, and these are the ergodic ones, and you have this two-stage sample procedure here. Yeah. So, and when we do our estimation, our sample averages converge to this ergodic component. They recover information about what ergodic measure you actually. Okay.
So, yeah. What do you mean by convexity in this setting? Like, what type of structure are you assuming on the distributions?
So in the distributions are measures, and the measures overall form a vector space, right? You can add them, you can form convex combinations. So probability measures, of course, are not a vector space, they're a slice in a vector space, right? But convex combination state is a slice. Okay. Right. Yeah. So you're literally forming convex combinations of probability measures. So you mix.
Okay.
Yeah. So another way of saying this is, like succinctly, this theorem is invariant distributions are mixtures of ergodic ones.
Okay, yeah, so in the mixture sense.
Yeah, in the mixture sense. Other questions on this? So then the last condition we have is something called conditional mixing. This is very technical to state, but informally what it means is the following. So if you think of mixing in Markov chains or in sequences, what the mixing property in sequences says is you have some random sequence, right? Starts at time 1 and then discrete time random process. Okay. So and now mixing says is some version of if I take the first element of the sequence or the first few elements, and then I take some segment later in the sequence. If I make the gap between those larger and larger, they're approximately dependent, right? So I can make dependence arbitrarily small by moving the segments far enough away from each other. So we need something like this here, except that we don't have a sequential structure necessarily, not in a field or graph or something. And so we need to figure out what it means to be further and further away from each other. And the way that works is in terms of the group, because these groups have a metric on them, and you can define that in terms of the metric. Yeah, so basically what we do is the tail, the second sequence, the second segment of the sequence that we move arbitrarily far out. We replace that by some subset of the group. We take some subset of the group and then take the segment indexed by that subset. So we apply all transformations in that subset to X, evaluate the function. Think of this as a stochastic process indexed by the set. Okay. So we look at this. And then we compare that to a pair of values. And the reason why we need a pair here and not just one is basically, I mean, roughly speaking, just because we put central limit theorems and those are second order results. So we need pairs. Yeah. So, and then basically we're saying, ignore this for a moment, we're saying those should become approximately independent if we move these two transformations here far away in the distance of the group from the set. Yeah. And and then it turns out that in this setup of ergodic decomposition, because we have ergodic decomposition, we can actually weaken this requirement considerably, because this independence only has to happen conditionally on the ergodic component, which is a much higher condition. So that's very pleasant. So so one example is for stationary Markov fields. This is like in stationary Markov fields, you have this thing called the de Bruijn condition for mixing, right? That is used in central limit theorems for Markov random fields. And if you have, that is exactly what you get to. So if this de Bruijn condition is satisfied, this condition holds even unconditional, and then even conditional. Yeah. So then now we've collected all these conditions here. So I'm kind of done at least explaining this result here. And it's now, I'm 45 minutes in. So should I stop now or should I talk about a few more examples for a few more minutes? How much longer should I go on?
If you carry on speaking and if I look.
Okay, all right. Well, I don't know, I'm always having to carry on speaking. Yeah.
It's always an extension.
Yeah, I can look out the window for a while in case anybody wants to walk out. So, all right. So let me show you one result that I'm personally, that's also in our paper, that is not a direct consequence of these theorems, of the theorem I've shown you so far, but that I'm personally very happy with. So this is a theorem that gives us a general central limit theorem for any form of exchangeability. So any random structure that is exchangeable, that is invariant under some form of permutations. And there's something here that you should know, and that is, so if I just page back to my theorem here. Here in the theorem that I've shown you, the scaling is square root of the size of the set. I mentioned that in the permutation case, we can choose the set here as a set of all permutations of n. So the scaling in the central limit theorem here for permutations, including exchangeable sequences and so on, would be square root of n factorial. That's a bit large, right? What we really get, we know from the basic center, like, I mean, the special case of the basic central limit theorem tells us square root of n not a factorial. So, and here we have square root of n. Okay, so the reason why this does not follow directly from this theorem that I've shown you is that in the case of permutations, this mixing condition is very hard to satisfy. I mean, you could, I think, probably piece something together, but we prove it in a different way. Basically, we start by proving some pretty far-reaching generalizations of the theorem that I've shown you, and then we can apply one of them and prove this. So, but what that's then the interesting thing is that that lets us completely eliminate the mixing condition. So we have a theorem here that's a bit more work, but we get a central limit theorem that looks like this with square root of n scaling when we average over permutations of size n, and it has no mixing condition. The only condition that it needs is a deterministic condition like this here. So this here is a transposition of entries ij, so permutation that just swaps two points somewhere. And we're taking a lim sup over one of these coordinates, right? And then taking an L2 norm. So in the L2 norm, there's an expectation here. This is a non-random quantity here, and then we're summing. And so basically what this condition says is it always holds if this function just depends on one or two elements or something, but if the function actually somehow depends on the entire random object here, it shouldn't, for instance, if it depends on an entire infinitely long sequence, it shouldn't depend too much on any one entry, basically. Yeah. So if it's too sensitive to putting something in one particular position, then we get into trouble. So, but basically we get a central limit theorem that looks like this. So basically exactly what you would write down, I think, if you would just guess something, right? And then we also have, here I actually wrote down the Berry-Esseen bound we get then. So that bounds the Wasserstein distance in this case between this here and the limit. And again, we get an expression that, I mean, without getting into too much detail, it's a very simple expression. That's kind of the message here. It's a very simple expression. In order to, I'm not accused of cheating, so usually the term Berry-Esseen bound is understood to bound the total variation distance, and here we're just bounding Wasserstein, which is meter and Wasserstein. Okay, so, and there's, I mean, special cases of this are known in various special, so for exchangeable sequences, this result, the special case for exchangeable sequences was proven by Bühlmann. So this is not Peter Bühlmann, the former editor of the Annals, but his father, Hans Bühlmann. He proved this in the 60s. And then for exchangeable graphs, a couple of authors have looked at that like over the last decade. So Peter Bickel and co-authors, and Christophe Ambroise and Christine Matthias in Paris. And then here for something called a jointly exchangeable array, there's a version by Egerson and Reber that goes back pretty far, but this requires stronger conditions. Yeah, they use a martingale central limit theorem, and you need these kind of conditions in the martingale central limit theorem that bound basically conditional variances. So
that the lim sup condition is not a mixing condition.
that's not a mixing condition. It's more like a noise sensitivity condition, I would say. So here's just some applications that we looked at in our paper. So one is for random fields. So if you look at a random field on a grid, you can make that grid either, I mean, literally a grid, so z to the power of d, or you can make it the random field on a plane or a Euclidean space, right? So in Euclidean space, we get something like this, where here I've written out the continuous case. I want a continuous example. Yeah? So here the group is not countable. And here we're averaging over a volume of length n in r-dimensional space, right? So it's basically exactly the continuous analog of what I showed you before, like moving this thing over the little grid, right? Here we move it over a block of volume, and we could also do minus n to n. That would be the exact analog of what I showed before. Here we just do 0 to n. That also works. Yeah. So for that, we get convergence. The version of that for Z is has been known for a while. That was proven by i.i.d. in the 1980s. And then we looked at one of our generalizations lets us make this quantity x here dependent on n. So each time we increase the size of the set we're averaging over, we're also changing x a little bit. That's something like, so in the classical case, so for i.i.d. sequences, that is something like what's called a triangular array. In probability theory, a triangular array is a Trinity theorem. And with that, we can prove something for random graphs that are stochastic block models with a growing number of classes. So this is like this exchangeable graph case or graphon case, but each time it's kind of like a non-parametric model where each time we make the sample larger, we allow the model to be a bit more complex. Then there's François Caron and Emily Fox introduced this random graph model, which is a little bit like a stochastic block model, but uses a Poisson process to generate a graph. So in that case, that leads to something that some authors have called the GraphX model. In that case, you sample in the Poisson process sense, which means you don't really collect endpoints. You take a certain area in the plane and collect all points of that area. So it's a random number of points that's Poisson distributed. So here we're scaling by not by the number of points, but by the size of that area. So okay, for that we can do a central limit theorem, and then one other application that I unfortunately don't have time to talk about, but that I'm very intrigued by is you can use this invariance idea to define entropy for a very large class of random structures, which is not a trivial thing in general to do. Yeah, but basically the same idea that you, like as in the estimator, that you have an observation window and you move something into that window. Something like that you can use to define an entropy. And that entropy, we can show that that type of entropy is asymptotically normal. So the empirical entropy that converges to something, the convergence theorem that I showed before, the law of large numbers, in this sense becomes the Shannon-Macmillan-Bryant theorem, right? And then we can show asymptotic normality with that. So just to wrap up, so basically there's an interesting hierarchy of conditions here. So I show you this ergodic decomposition result that tells us convex set ergodic distributions are corner points, then the law of large numbers Lindenstrauss, and then our results here. So, and there's two types of conditions. One are conditions on the group, and the other are conditions on the distribution. So in terms of conditions on the group, for ergodic decomposition, we need that it's locally compact set count. And okay, and Hausdorff, that's usually small, right? I like to write that. So for the law of large numbers, we need the same thing plus amenable. And then for the central limit theorem, we need the same thing plus amenable, plus we need the metric on the group. We need to choose a specific metric because we need the metric to define x. Right? I mean, in a rate of convergence result, you always need some kind of metric somewhere, right? So here the way it enters is the mix. So and then for a Berry-Esseen bound, which bounds the speed with which that happens, right? Basically the same thing, and then I've written in parentheses plus geometry here. So that is basically because you don't need anything to say anything specific about the geometry beyond the metric for the theorem to hold, but the size of the bound, so the function that upper bounds it, that depends basically on the size in a certain way on how the metric falls in this group rule. Yeah. And so then conditions on the group, you need for the ergodic decomposition, you just need invariance of the distributions. For the law of large numbers, you need a first moment. Okay, you're estimating expectation, right? For the central limit theorem, you need invariance, the second moment, and this mixing condition. And then for the Berry-Esseen bound, you need 4 moments and the mixing condition. Yeah. So, and then let me just finish with like this part here. So one observation that I've already made is the asymptotic variance is always come out of market. That's just an empirical observation. That just seems to be that somehow like, I mean, we know from in many ways in mathematics, as soon as you have a group in there somewhere, things become very clean, right? And that seems to happen here in this form. For for those of you who are into, if anybody here is into proving CLTs for random structures, this is a question that we also got from our reviewers. Is you need a stable. There's a type of condition that's called stable convergence. That is usually assumed if you prove something like central limit theorem, Orbanz or something like that. And we don't need that here. And the reason why we don't need it is ergodic decomposition. This conditional ergodicity structure and ergodic decomposition that basically saves us from this condition. And one thing that we can show, that we can see explicitly in this results, is the more symmetries we have, the faster the rate gets. So one way you see that is in the growth of these Fellner sets. But for instance, like when we started giving talks about this, when there were probabilists in the audience, we were often asked, okay, so what your result says that is in the graphon model, the exchangeable random graph model, you get a convergence rate of square root. But the i.i.d graph is exchangeable, and there we already know that the rate is actually n square root. The result for that is the reason for that is that the i.i.d graph has more symmetries. It's invariant under a larger set of permutations. Arbitrary the graph because it can that is the size of that is quadratic. That's quadratically more symmetry than an arbitrary exchangeable graph. But basically the proofs are an adaptation of Stein's method, and that is really so Stein's method adapts to these. I mean, we have to modify it a little bit because it's not applicable out of the box. It basically so Stein's method. We build something called dependence neighborhood, which is basically around the variable you build a neighborhood, and you only have dependence with that neighborhood. And that is not the case here. Our dependence bleeds out of that neighborhood, and then we have to use this mixing condition control. So, but overall, Stein's method adapts to this, as it was. And okay, I'm going to stop. That's it. So thanks very much. Thank you.